Hello, and welcome again to another series of lectures in real analysis. So for this series of lectures, we will discuss the fundamentals of Lebesgue integration theory. So to those who are not familiar with the Riemann integral, which is the integral that we used in elementary calculus, we provide a review in the first lecture. So to recall, what is the geometrical interpretation of this integral? So this is the integral of f over the closed interval AB. This is the signed area of the region bounded by the curve y equals f of x. So that is the graph of your function. The vertical lines x equals a and x equals b, and the x-axis. So basically, this is the shaded region in this drawing. So it's a signed area in the sense that if the region is above the x-axis, you have a positive sign. If the region is below the x-axis, you have a negative sign. Or in other words, you subtract the area. So therefore, the integral over this function f, say a continuous function f, over the closed interval AB, is, at least in this figure, the difference of a plus and a minus. So that's the geometrical interpretation of the area, or the Riemann integral, I should say. Well, to obtain this area, what we did is to consider the following scenario. So first, we partition the closed interval AB into smaller subintervals. So let us denote by the left endpoint A to be x sub 0. And let us say we have 5 subintervals and denote B to be x sub 5. And then we introduce points between the two. In this case, we have x1, x2, x3, and x4. When each subinterval, say on the subinterval x sub 0, x sub 1, we choose a point on the closed interval, say z sub 1, that will determine the height of the approximating rectangle. So we approximate the area of this region by this rectangle having the height which is determined by the function value of z sub 1. And that is f of z sub 1. We do this for the rest of the intervals. So we have taken z sub 2 here, z sub 3, z sub 4, and you can choose the point z sub 5 to be an endpoint. So in this case, we choose it to be the right endpoint x sub 5. This will determine the heights of the rectangles. And in this way, we can approximate the signed area as the sum of the areas of the rectangles. And this will be the following sum. So this is the sum, let's say from k from 1 to n, in this case 5, of the height f of z sub k times the length of the base, which is x sub k minus x sub k minus 1. So this will be your height, and this will be the length of your base. Of course, here you have some sort of overestimations provided by these regions here. And you have certain underestimations. So for instance, these regions here, where the area is not included. Of course, we have a better approximation if we choose a smaller partition, or in other words, we subdivide the interval AB into further smaller subintervals. So with this discussion, let us define formally the Riemann integral. So let's start with a bounded function, say f, defined on the closed interval AB, and it is real valued. Okay. Now we define a partition of the closed interval AB to be a sequence of nodes or points, say x sub k, k from 0 to n, in such a way that this sequence is strictly increasing. So x sub 1 is less than x sub 0 is less than x sub 1, and this is in turn less than x sub 2, up to the last point x sub n. And the initial point x sub 0 is the left endpoint A, and the last node x sub n is the right endpoint B. So here we have, let's say, n subintervals. So in the previous drawing here or figure, we have n equals 5. We define the largest length of the subintervals induced by the partition to be the norm. So the norm of a partition say P, having these points x sub k, k from 0 to n, is defined by and will be denoted by this, okay, similar to our notation for the Euclidean norm. So the norm of the partition is nothing but the largest length of the subintervals induced by the partition. So this is the max of the x sub k minus x sub k minus 1, k from 1 to n. So again, this is the length of the kth subinterval x sub k minus 1, x sub k. Here I'm only referring with the difference, okay, induced by your partition P. So basically, the norm of a partition is nothing but the largest length of the subinterval induced by your partition. Okay. Now, going back to this. So this is an approximation of your integral, and this is what we call a Riemann sum. So given a partition P and a bounded function f, a sum having the form, okay, and which we denote this sum by R, let's say Rf, your bounded function, your partition, and some representative points x sub k, k from 1, z sub k, k from 1 to n. So a sum of the following form, which is the sum of the signed areas of the rectangles, where z sub k is an element of your kth subinterval, will be called a Riemann sum. So this is basically the generalization of the one that we discussed a while ago. So based on this, we are now in position to define what do we mean by a Riemann integrable function. So we have the following definition. So a bounded function, say f, on the closed interval AB with values in R is said to be Riemann integrable if we can find a real number, say R, such that given any positive epsilon, there exists a delta, which in general depends on epsilon, and it is positive. For which if you take any partition, say P, having the nodes x sub k, k from 0 to n, of AB, with norm less than delta, and for every, let's say, representative points z sub k that will determine the height of your kth rectangle. Here k is from 1 to n. We have, so think of this R as your signed area. So the difference, or the absolute difference, between the signed area and the Riemann sum generated by this partition and these representative points z sub k's, so the absolute error is less than epsilon. So roughly speaking, this means that if your norm is small enough, then that would imply that the subintervals are also very small. The Riemann sum and your signed area is close to each other. So this is your absolute error between the signed area and the Riemann sum. So you can, so for Riemann integrability, you can find a delta in such a way that the Riemann sum is close to your signed area, in the sense that the absolute error is less than a given positive epsilon, as long as the norm of your partition is small, in the sense that it is less than delta. So in this case, By this, we mean that your bounded function is integrable. We write that R is the limit of your Riemann sums as the norm of the partition goes to 0. And this limit here is what we denote by this group of symbols. So this is the Riemann integral of f over the closed interval AB. So that's the definition of your Riemann integral for bounded functions. So this definition is somewhat flexible in the sense that you can choose any, okay, as long as your function is Riemann integrable, you can choose any representative z sub k in each of these subintervals. However, this flexibility also gives us the difficulty at the same time in proving Riemann integrability for a given function, because you need to prove that this is valid for any representative on the closed subinterval x sub k minus 1, x sub k. So without going into the technical details, and all of this can be seen, for instance, in our course notes. I will provide some remarks for this Riemann integral that you are probably might familiar of. So first, if the Riemann integral exists, then it is unique. So the proof is that suppose you proceed in a classical way. Suppose you take two Riemann integrals, and by that you might have different partitions, okay, and then you take the refinement of the two partitions. In other words, you take the union of the nodes between the two partitions corresponding to the two Riemann integrals, and you show that this difference, the difference of the two Riemann integrals, can be made arbitrarily small. So the main idea here is to use refinement. That is, by combining the nodes of two partitions. So another remark, a continuous function on a closed interval, on the closed interval AB, is Riemann integrable. And well, the idea, the proof, is to use the fact that a continuous function on a compact set is uniformly continuous. So proving Riemann integrability in this case, use the fact that a continuous function defined on the compact set, which is the closed interval AB, by the Heine-Borel theorem, since this is closed and bounded, therefore it is compact. And from this, a continuous function on this closed interval is uniformly continuous. Likewise, a bounded monotonic function. So a monotonic function is a function that is either increasing or decreasing on the closed interval AB is Riemann integrable. The second property is what we call monotonicity. So if, let's say, you have two bounded functions, f and g, and f is less than or equal to g on the closed interval, provided that these bounded functions are Riemann integrable, then the integral of the smaller function is also less than or equal to the integral of the larger function. So geometrically speaking, let's say you have a function g, which is larger or equal to some function f. And then integrating this over the interval AB, so this, let us say this is x equals a and x equals b. The area of the region determined by your function f. In this case, this is the region colored by red, is smaller than the region determined by your larger function g. In this case, this is the shaded region blue. So this will be your integral over f over g, and this will be your integral over with respect to f. So again, the area of the smaller function is less or equal to the area of the larger function. So the inequality is preserved under Riemann integration. Next, we have the so-called linearity. So for, let's say I have two real numbers, alpha and beta, assuming that A and F are Riemann integrable, then the linear combination, say alpha S plus beta G, which is again a bounded function, is also Riemann integrable, and the Riemann integral is the linear combination of the Riemann integrals. Of course, by induction, you can prove this into any finite linear combination of Riemann integrable functions. The next is what we call additivity. So for any C in the open interval AB, integrating F over the closed interval AB. So if F is Riemann integrable on the closed interval AB, it is also Riemann integrable over the closed intervals AC and CB. And the integral over AB is the sum of the integral over the closed interval AC and the integral over the closed interval CB. So again, let's say we have a function y equals f of x, and let's say this is A, this is B. So taking the area bounded by the curve y equals f of x, the x-axis, and the lines x equals A and x equals B. Well, this is the same if we partition the area into two parts and say you have a point C and you divide the area into two parts. So in this case, you now have this region, which is the integral over AC. And on the other side, you have this region and this region here would be the Riemann integral over the closed interval CB. So if you take the sum, you get the integral from A to B. And this is additivity with respect to the domain of integration. So in other words, the Lebesgue integral over the closed interval is the sum of the Riemann integrals over the subdivision AC and CB. Okay, so going back to the definition of the Riemann integral. So here we need to check, or we can choose any representative point z sub k on the closed subinterval x sub k minus 1 and x sub k. So to test Riemann integrability, in fact, it is enough to consider specific sums wherein we take this z sub k's to be the largest height in the or the largest function value provided that it exists, and also the smallest function value. So in that case, you will have circumscribed rectangles and inscribed rectangles respectively. So we call those specific Riemann sums to be Darboux sums. So named after the French mathematician Darboux. So there are two versions. We have the upper Darboux sum, and we denote this by U. Fp with respect to some partition P. So this is the same Riemann sum, but instead of taking the specific function value at one representative, we take the supremum of f of x on the closed interval x sub k minus 1, x sub k. And this will determine the height of the kth rectangle. And still you have the length of your subinterval. The supremum exists because f is bounded. And in a similar note, we have the so-called lower Darboux sum, denoted by L, F, P. So the same definition, but instead of taking the supremum, we take the infimum. Again, this exists due to the fact that f is bounded. Okay, so here we take a specific form of sums. So you can think of this as circumscribed rectangles and inscribed rectangles. And there's, in fact, the following theorem. So suppose that, or let us take a bounded function, f on the closed interval then f is Riemann integrable if and only if the smallest or the infimum of the set of all upper Darboux sums generated by any partition of AB. Here we denote by script P of AB to be the collection of all partitions of your closed interval AB. So if the infimum of upper Darboux sums is the same as the supremum over all partitions of AB for the lower Darboux sum. So this is, in fact, it can be used as an alternative definition of Riemann integrability. So you need to show the infimum of overall upper Darboux sums is the same as the supremum of the lower Darboux sums. So you can think of the upper Darboux sums as some sort of overestimations, and the lower Darboux sums as some underestimations. So here you can squeeze the area in between. So that's the basic principle. And this is in fact introduced by Darboux, and this condition here is what we call Darboux integrability. So if the infimum of the upper Darboux sums is the same as the supremum of the lower Darboux sums, then we say that your bounded function is Darboux integrable. So according to this theorem, Darboux integrability and Riemann integrability are the same. And in fact, the properties or the remarks listed here, the 3 remarks listed a while ago, can be shown using that theorem. So to show Riemann integrability, it is enough to establish this equality or this Darboux integrability. And this is far more convenient than the usual definition or the first definition of Riemann integrability. So I will not give the proof here. Those who are interested, you can look at the appendix of our course notes. In the introduction, we mentioned that the Dirichlet function is not Riemann integrable. So to illustrate that, okay, so first let us recall the definition. So Dirichlet function on the closed interval AB, say f, denoted by f, has 2 values. So it's either 0 or 1. So if x is rational, then it is 1. Otherwise, it is 0. So you can think of f as the characteristic function or the indicator function of the rational numbers on the closed interval 0 to 1. So now let us pick a partition AB, and let us say that it has nodes x sub k, k from 0 to n. Now, for each k from 1 to n, take note that x sub k minus 1 is less than x sub k. So between 2 real numbers, you can find a rational number, let's say q sub k, and an irrational number. Let's say qk prime. So here q sub k is rational, and q sub k is an irrational number. So let's say this is your subinterval x sub k minus 1 and x sub k. You can find a qk, a rational number between the two, and an irrational number between the two. So with this, this implies that the infimum of f of x in the closed subinterval xk minus 1 xk. So here, recall that f is either 0 or 1. So the infimum is either 0 or 1. Since we can find a rational, an irrational, let's say q sub k prime. So the value 0 is attained at qk prime. So this would be f of q sub k prime, and this is 0, since q sub k is irrational. And in a similar note, the supremum is attained at q sub k and when evaluated at the Dirichlet function, it is equal to 1. So what are the implications of these equations? So the first one implies that the lower Darboux sums is always 0. On the other hand, the second set of equations implies that the upper Darboux sums is 1. Take note that P here is an arbitrary partition of AB, so these equations here holds for all. These are valid for all P in the collection of all partitions of AB. So therefore, if these are valid for all partitions, so taking, let's say, the supremum over all lower Darboux sums, so the supremum would be 0. On the other hand, the infimum over all partitions of the upper Darboux sums is 1. So these two are not the same, clearly not the same. Therefore, the Dirichlet function f is not Riemann integrable according to our previous theorem. The one we stated here. So if this equation here, the infimum of u is the same as the supremum of L, then you are Riemann integrable. And vice versa. So if these two are not equal, then your function is not Riemann integrable. So this very simple function that takes either values 0 or 1, depending whether the input is or the argument is rational or irrational, is not Riemann integrable. So that's one limitation of your Riemann integral. There are certain simple functions. For instance, this one. By simple, just think of it as the usual definition of the word simple. We have a simple function, the Dirichlet function, which is not Riemann integrable. So this example is in fact related to a more general theorem. So the following theorem states that a bounded function on a closed interval AB is Riemann integrable if and only if the set of points where your function is discontinuous has Lebesgue measure 0. So put in another way, Riemann integrability is equivalent to the statement that your bounded function must be continuous almost everywhere, or that is continuous except on a set of measure 0. So this is a complete characterization of Riemann integrable functions. So applying, for instance, this Dirichlet function, one can show that this function is discontinuous everywhere. In other words, all points of the closed interval 0 to 1 are discontinuities of the Dirichlet function. So the set has measure, Lebesgue measure 1. Since that is not equal to 0, this theorem also says also tells you that the Dirichlet function is not Riemann integrable. So as usual, I will not provide the proof. The proof is given in the course notes again, and it requires some technical concepts, such as, for instance, the concept of oscillations. Okay, so you can think of oscillations as some sort of related to discontinuities. So the concept of oscillations can be used to prove this theorem. So the proof is given in the lecture notes, as I said. So those who are interested, you can look at that proof. Okay, so based on this example, you want to derive or define a more general theory of integral for which this integral can be this Dirichlet function can be integrated, or the integral exists, and this will be built on the Begg measure, or in general the measure theory that we have discussed in our previous lectures. And in the next lecture, we will discuss that a general integral called the Lebesgue integral and the main ideas in its construction.